Hi, good morning to Guan Yu, Ziwei, and Wei Xiang. Okay. Polly is very surprised to see many of you getting up this early. Interesting. Are you all staying home? That's probably the reason. All right. So today, and good morning, Zhao Qi and Jimmy and Yo Yu. Wow. Glad that pretty much all of you made it today. That's a little bit odd. Polly was not expecting this towards the end of the semester. I got up too, but you see that, I am the older people. Yeah. So you guys, I know, I was young once. So yeah, it was hard for me to get up early. Interesting. All right, and you know what? There's not more to announce, and let's go ahead and start with the topics today. Yeah, we are gonna have a handful today. Yeah, you see that there'll be lots of quizzes today. And let's start from link state routing. Okay, because we already talked about the algorithm of link state routing, which is Dijkstra, shortest path algorithm. So the next few videos are more to talk about the issues of Dijkstra. So the issue of link state routing using Dijkstra. First is to analyze the performance, the computation complexity of the Dijkstra algorithm. Now with the two examples walked through, you see the Dijkstra's algorithm, although look a bit cryptic at the beginning, it's in fact quite straightforward. Initialization phase, 2 steps. Looping phase, 2 steps. Looping phase is the one that we take multiple iterations, we spend more time with. So that is going to bound the complexity of the Dijkstra algorithm. And within the looping phase in each iteration, which of the steps is taking the most time? Yeah, the second step. Inside the second step, we're actually checking all nodes J. Okay, that is adjacent to the node we just added into N prime. Okay. And inside each iteration in the inner for loop, what we do is this, the mean operation. And this is in fact to compare the value of the current shortest path to the newly discovered path, right? So D to I plus the link cost between ij. So it's a comparison between this value and this value. So you have the looping phase, and inside there's an inner loop that is doing a lot of these value comparisons. Now, if we consider a fully connected network, that is the worst case for Dijkstra algorithm. Inside the network, there are n nodes. In the first iteration, so only the source is in the n prime. How many j's is connected to the source? Yeah, it's fully connected. Therefore, n minus 1 nodes. They will all be j, and we'll need to do mean for each of these j. First iteration, we'll need to do n minus 1 comparison. Second iteration, how many? Because there's one more node being included into n prime. So number of j in the second iteration, only n minus 2. Third iteration, and we can go on until the second last iteration, we have only one node remaining connecting to the new node being added to the n prime. In the last iteration, the second step is not going to be called because there's no j remaining. So if we add all these together, this is the number of comparisons. N multiplying n minus 1 divided by 2. And this is in the scale of n squared, big O n squared. So big O here is actually to say that the Dijkstra algorithm in the worst case runs in the scale of n squared. That means the time complexity, the growing trend of Dijkstra algorithm is this. When n approach where the network goes really big, the time requirement goes in this trend, like an n squared curve. Now, if it's only big O n, the curve is linear, a straight line, sorry, the line is not very straight here. Now, there's an implementation available for Dijkstra algorithm such that we could do away with only n log n. Now, this is better than n squared. So again, n is here, n squared growing really fast here, and n log n is actually kind of in between. Faster than the pseudocode we've investigated, and better than a linear algorithm. So Nice to have an efficient implementation, even though the original Dijkstra algorithm is not so good.
All right, so that was also Dijkstra's computation complexity. Next issue is about link cost. If you recall yesterday, we talked about one can use delay for the link cost, one could use also traffic low for the link cost, right? So if we use traffic low as the link cost, it's actually quite nice because then every time we choose a route, that is the lowest in traffic load. But if you use traffic low as the link cost, that means also that you might also be adjusting the link cost as traffic being added or traffic disappears. And when you do that, setting link cost dynamically, you might run into this problem called link or path oscillation.
There's one very special issue with link state routing that's called the path oscillation problem. And it happens when we set the link cost dynamically based on the amount of traffic going on the link at the time. Now let me explain using an example. Okay, so we have 4 nodes in the example, A, B, C, and D. A is the traffic sink. Okay, all traffic goes to A. B, C, D are traffic sources. A generates one portion of the traffic and send it over past BA. E generates E portion of the traffic. E here is a very small amount, much smaller than 1. And C is taking the CBA path to send traffic to A. D generates also one portion of the traffic and it's taking path DA to send to destination A. And at this point, we need to update the link cost based on the traffic going on the link. So for link DA, amount of traffic is one portion. For link BA, amount of traffic is what? One portion plus the E portion from C. So total cost, 1 plus E. The cost for link CB, amount of E traffic from C only. You see also here, okay, this direction, BC, there's no traffic, therefore link cost is 0. Similarly for AB, similarly for AD, and similarly here for both direction in link CD. So we finish updating the link cost. After a while, link state routing is going to trigger Dijkstra algorithm running again. Right? As I described, link state routing is a dynamic routing algorithm. We do periodic update, and sometimes we use also network events to trigger recomputation of the routes. Link state routing there does periodic recomputation. Okay? It's going to recompute the routes based on the link cost now. So let's see. B here, we'll see 2 possible paths to go to A, right? One is to go counterclockwise to A, the other clockwise to A. So this direction here, the cost is what? 1 plus E, because there's only one link and the link cost is 1 plus E. If we take this other path, B, C, D, A, yeah, the path cost is the sum of the link costs, 0 plus 0 plus 1. Okay, so if we take the clockwise path, okay, to go from B to A, cost is only 1. And this is 1 plus E, therefore B is going to choose to go this way to send traffic to A. C, also see 2 possible paths. Okay, if we take this direction, cost is E plus 1 plus E, and that is 1 plus 2E. The other direction, cost is 0 plus 1, therefore 1. And therefore, C would choose to go also clockwise to send traffic to A. Similarly, D sees also 2 paths. Okay, this direction here, cost is 1. This direction, 0 plus E plus 2 plus E, 1 plus E. So altogether, 1 plus 2E. So still, okay, this direction better. So D is also going to take the clockwise path, okay, the same path to A. So after the route computation complete, you see B, C, D all change to send traffic clockwise. And then we need to update the link cost again, right? So given the previous cost, we come up with the new routes, and we will then, okay, update the link cost, and we come to the new cost again. What is the new cost now? Okay, on link BC, there's only one portion of the traffic. On link CD, 1 plus E. On link DA, 2 plus E. And that is why we see 1 plus E, 2 plus E, and all the rest of the links, 0. Once we update the link cost, after the next period that the Dijkstra algorithm is triggered, we compute new routes. So B will then try to see the cost to go this direction and the cost to go the other direction. The cost going counterclockwise is now 0. Cost going clockwise is now 1 plus E plus 2 plus E. That's 4 plus 2E. So dominantly, BA is the better path. C's cost going this direction, 0 plus 0, cost is 0. The cost of the other direction, 1 plus E, 2 plus E, 3 plus 2E. So C is going to switch going this direction to send the traffic. What about D? Going this direction, 0 plus 0 plus 0. Going this direction, 2 plus E. So D is going to switch for the first time to go counterclockwise. And that's why in the next moment, you see traffic beginning to change direction completely. Okay? From all clockwise, okay, one period before, to counterclockwise the next period. So given these new costs, we calculate the new routes all going counterclockwise, and we update the new costs again based on the traffic. DC is now 1. CD is now 1 plus E. And BA now 2 plus E. And that is what you see here. 1 plus E, and 2 plus E. As a result, B sees this pass costs 0. This pass costs 2 plus E. B switch the other direction. C sees this pass, really high, 3 plus 2E. And this other direction, 0. D, this direction, 0. This direction, super bad, 4 plus 2E. So all of them would switch back like this. And the link cost gets updated again. 1 on this link, 1 plus E on this link, and 2 plus E on this link, which is identical to 2 periods before. Okay? And you see the next period is going to be like, the previous period. And the traffic is going to oscillate infinitely, right? Clockwise, counterclockwise, clockwise, counterclockwise. So that is the path oscillation problem if we set link cost dynamically in link state routing. Okay, that's running the very straightforward Dijkstra algorithm. Just be careful here.
All right, and the next video is about 2 issues. One is after we learned about the LS link state algorithm being using Dijkstra, in the end of the computation, we managed to find the shortest path tree where the root is the source. You see that the goal of these routing algorithms is that sitting at the control plane of the network layer, after the computation, we're supposed to come up with the forwarding table so that we could insert to the data plane, so that the data plane router can figure out exactly when a packet arrives, which network interface to forward the packet further out. Okay, so how does one generate that forwarding table? Okay, the second issue is, using Dijkstra algorithm, we kind of assume that we know the graph of the network already. Yeah, so how does the router in the control plane get the graph of the network at the first place? Okay, so link state routing, there is a mechanism inside that is allowing each router to figure out what the network graph is. Okay, so these are in the next video.
To put simply, link state routing works this way. Each router implements the routing algorithm. It's going to wait until the total information of the network is in place. Then it calls the Dijkstra algorithm. At the end of the calculation, we get the least cost path from this router to every destination possible in the world. So that is essentially the shortest path tree. Now that router being the root of the shortest path tree, we'll see there are multiple branches out to the rest of the world. Taking one branch, it gives you the shortest path to a certain set of destinations. Another branch to another set of destinations. yet another branch to yet another set of destinations. And so from the tree structure, okay, we can construct the forwarding table, and that is how the forwarding table is calculated in the control plane. Next is just to install it into the data plane. Now, the only part I'm going really quick without mentioning much is this: how we get the total network information so we could apply the Dijkstra algorithm in the first place. That is done through this link state broadcast. Each node, okay, in the network is going to generate link state report based on very local information. That includes the ID of the node itself, the ID of the immediate neighbors, and the cost, okay, on the link to these immediate neighbors. Okay, so these are the local information. Node, the neighboring nodes, and the link cost to the neighboring nodes. So all these local information is going to be in the link state report coming from the node. This link state report is going to be broadcasted, meaning, okay, going out through the entire network, being received by all other nodes. So all nodes eventually will receive link state reports from every other node. Okay. And these link state reports from every other nodes, including the node's local information, is going to be used to restore, okay, the total network. Let me give you an example to illustrate how that is done. We have a very simple network here, only 4 nodes. Okay, you see, U connects to V, U connects to W, U connects to X. Okay, so if we are node U, okay, and generating node U's link state report, it's going to contain this: the ID of the node itself. Yeah, there are 3 neighboring nodes, V, W, X, and the cost on the link to these nodes, 5, 3, 7. So U to V, link cost 5. U to W, link cost 3. U to X, link cost 7. Similarly, V is going to generate its link state report, which is going to contain only 1 entry. It connects to U, link cost 5. The link state report from W should look like this: 2 neighbors, U and X, cost being 3 and 2. Link state report from X is contained 2 entries, U and W, link cost 7 and 2. So each of these nodes, U, V, W, X, is going to broadcast their link state report, and every node in the network is going to receive its own local information and every other node's link state report. Therefore, node U here is going to receive the link state reports from V, W, and X, which we know already look like this. The way to restore the network topology is this. Okay, node U knows the local information. It connects to V, it connects to W, it connects to X. Cost is 5, 3, 7. Now, seeing node V's link state report, knows that V and U is connected, cost is 5. V, U, I'm U, so I know, okay, and the cost is 5. W's report is going to tell, okay, the cost to U is 3, which you already know. Oh, W is also connected to X with link cost 2. So W connect to X, link cost 2. X report says I connect to U, so X connect to U, you already know. X reports also that it's connecting to W, link cost 2, which you already have. And you now manage to reconstruct the total network information from receiving link state reports from all the nodes in the network. And it's contributing also so that other nodes receiving used link state reports can also reconstruct the total network. So you see this one here, U connecting to VWX. Yeah, isomorphic, okay, of the network there.
All right. So next video is about another complexity in an algorithm. It's called the memory complexity. So link state routing there using Dijkstra, assuming the full graph being available. We saw in the previous video that how we get the full graph. But the thing is that what is the cost keeping the full graph?
So that was the last piece of the puzzle, link state routing. Other problems you see here. Now you know a little bit about the link state broadcast. Yeah, some of you might see this. These link state broadcasts, it's going to travel the entire network. And it's coming from every router, right? So you have n copies of these packets going to n nodes. The bandwidth consumption is again at this scale. And to store the topology information in the router, right? So we discussed the complexity of Dijkstra algorithm. We only talk about the time complexity. We have not yet talked about the space complexity. it's also huge, right? In the worst case, you have n nodes fully connected to every other node. Then you have what? N square number of links. You need to store costs, okay, for all these links. Ugh. Not very scalable when the network goes big, when n goes large.
And that was exactly the reason that there needs to be another routing algorithm that the internet runs. It's called the distance vector, in short, DV routing. All right, and that probably use a sequence of quizzes to try to introduce distance vector routing, because this type of routing algorithm is a little bit harder to understand. It's a little bit counterintuitive. I guess it's probably because that somehow human being thought that we are God. So let's start from the first quiz in the series. This is quiz 39. All right. So now you need to, do some role play, pretending that you are a router. Okay, suppose now you are router X. Okay, so you see that in this network, very small. Okay, XYZ only 3 nodes, and you are router X. And suppose you have some data you want to send to someone out there, W. Okay, you know the link cost from yourself to Y being 9, and the link cost from yourself to Z being 4. Okay, and router Y, one of your neighbors, tells you, I know a way to go to W. But router Z tells you, I have no idea how to get to W. Okay, now being router X, how would you pass the data to Y or Z? And why? To answer the question, I would suggest let's go to the Slack space. And you should find channel W14, quiz 39. Oh, okay. I've already seen some of you answering the questions. Yeah. Very, very interesting. Yeah, again, as I said, human beings like to think that we are God. We see everything. In fact, you do see everything, right? If you are still a student looking at the slide. But if you are a router, I know, it's a little bit controversial. But I think this is great. This is great because you guys are showing different perspectives. So you see here, Team Huaizhi, Team 7, saying, I was sent to Y because Y tells router X, Y knows a way to go to W, right? So Huaizhi was thinking that, hey, it's safer because at least Y knows a way to W. And Z says, I don't know. So the chance of the data getting to W, it seems, right, higher going through W. But Keke down here, Team 10, is sending to Z because we know a path from Z to Y. Because we see from the graph, there's a path from Z to Y. And Y says, I know a way to W. Yeah, this is assuming that X knows that that's assuming that X somehow knows Z has a path to Y. But you see, at this point in time, Z only say, I don't know a way to W. And Z did not say that I know a way to Y either. So I think Keke here is demonstrating perfectly how human thinks. But unfortunately, right, routing algorithms runs on a router. Okay, inside a router can only make a decision based on what the neighbors told them. The router doesn't see the entire graph that we have on the side. But Keke, this is great. I love it. I love that you tell straight from what you think the answer should be. And you are right? From the perspective of a student looking at the whole graph. Okay. Yeah, so let's see. Cai Tong here, thinking at the same perspective. So in case X knows there's a way from Z to Y, then of course X then send it to Z and have Z send it to Y. And I forgot to tick Huaizhi's answer. In team 5. Okay, so team 5. Very good, Jiahong. You are role-playing. Well done, role-playing being router X. Yeah, given the very, very limited information you have, yes, you pass it to Y because Y is the only neighbor saying that at least I know a way to W. I think Jimmy here is saying the same thing that team 10 is saying. Pass Y. Yeah, Howard. Very good. Pass Z and Y since the route passing Z. Okay. Yeah, I see. And you also see. Okay. At this point, you actually don't know. As X, nobody tells you that there's a path from Z to Y, in fact. Okay, all that's being told is Y tells X there's a way, and Z tells X there's no way to W. Yet you know you're connected to Y, you know you're connected to Z. Okay, you as router X. All right. All right, guys. Being a routing algorithm or being a router, you can only make decision that you know of. Being a router X, you don't know that there's a path between Z to Y until you're informed. So at this point, all the information you have is just router Y tells you I know a way. Router Z tells you no idea, and that's all. All right, so Keke, Cai Tong, Bo Ru, and You Yu. Yeah, so you guys are thinking, again, like a human beings. The router doesn't know yet. Okay, there's a path from Z to Y. And you certainly don't know the causes too. You know the cause to Y, you know the cause to Z, and you get information from Y and Z. Y did tell you something, Z did tell you something, but they did not tell you about this link between the two of them. So if you look at the graph, as human beings, you know a lot more. But as X, from X's perspective, it's very limited. All right. But you know what? That's okay. Let's do more exercises so that you get used to that things can be very different if you change the perspective. Okay. And the reason that we have so many quizzes here before we can start talking about distance vector routing is exactly this. Okay. You will feel that distance vector routing is a little bit stupid. Okay. But think again, distance vector is just a routing algorithm that's each router is a little bit less informed or informed in a delayed way. All right. So this is a quiz 40. You see the same network. Again, you are asked to play the role of router X. All right. And this time, Y tells you, I know a way to W, and the path cost is 3. And Z tells you, I know a way to W, and the past cost is 2. Would you pass the data to Y or Z? And why? So in a way, you guys all pass quiz 39 because you tell me why. And from the reason that you make the decision, I see that you assume you know there's the link between Y, Z, and the causes too. And of course, let's go to Slack space. And this is W14 quiz 40. Let's see. I would pass, Team 5 here says I would pass the data to Z because Z knows a way to W and it has a lower cost than Y. Okay, so you will pass it to Z and Z tells you the cost is 2 and plus 4, the cost from X to Z, so the total is 6. The link cost from X to Y is 9, and Y tells you the cost from Y to W is 3, so 9 plus 3, 12. Yeah, so Jiahong, I totally agree. I totally agree. Very good. I see your teammate is very supportive. That's good for you. Team 7, pass to Z. Yeah, because the cost is 4 plus 2, right? 4 is the link cost from X to Z. And Z says the cost to W is 2, together 6. And this is lower than passing to Y, which is 9 already. And the cost to W from Y is 3, together 12. So 6 much lower than, 12. So I guess for this question, it's quite clear, isn't it? Pass to Z. Very good. Very good. And again, at this point, we don't know that there's a link between Y and Z yet. Very good. Well, even if we know that there's a link between Y and Z, you still choose what? Z. Right? Because if we go X, Z, if we are not now God again, then it will be X to Z 4, Z to Y 2, and Y to W 3. That adds up to 9. But X, Z, and then straight to W is only 6, right? That is still too long. Yeah. So I see here, actually somewhere earlier, I think Boru here is the one first demonstrating that you get it. We don't know the link between Y and Z, and you make decision only compare X, Z, W, the cost, versus X, Y, W, the cost. Perfect. Okay. It is, Youyu. Yeah, through Z, that is the lowest cost. And Shen and Howard here, yeah, comparing only these two possible paths because you only know these two possible paths. You as router, not as a human being, okay? Cai Tong, there you go. Very good. Hui Xing, there you go. Okay. Good. So I think it's a good time now. Let's move on to quiz 41. So this time, the same graph, the same network, but Y tells you something a little bit different, and Z tells you something a little bit different. Y says the cost to W is only 2, and Z says the cost to W is 3, a little bit higher. Would you pass the data to Y or Z? Again, we still don't know. There is a link between Z and Y. Very good, guys. Very, very good. Yeah, still you compare the two paths, xyw to xzw. Right, so through y we have 9 plus 2. Through z we have 4 plus 3. Yeah, we still send it to z because that's all we know of. Very good. And you know what? That was the idea. Okay. But to illustrate more, let me go here. Yeah, so this is to make sure that the idea is very, very clear. So there's quiz 42. So what do we see here in the center of the picture? It's an elephant, isn't it? But you see that we have these scientists that are blindfolded, okay? And they're actually looking at different parts of the elephant. Okay, so the one, let me use a laser here. Yeah, the scientist at the top, right, touching the ears, finds, oh, okay, this might be a fan, right? And the scientist at the tail feels that, oh, this is a rope. Okay. And of course, the scientist on top of the letter is feeling that there's something flat and wide and broad, almost like a wall. Okay. And you see that the scientist being blindfolded, okay, and only see from their perspective, or only feels from their perspective what the object is. They give you different answers. Yeah, that's called the perspective. At different perspective, you have different perceptions. Okay, now let's try this, guys. The quiz is finally coming. So let's try to guess what the object is, given the hints from blindfolded users or testers. So the first tester, try the object out. Okay, and the first tester says, this is a drink. Second says, it's cold. And then the third, fourth, and the fifth says, oh, it's sweet. And there's something soft inside. And it feels a little bit chewy. So what is this, guys? Yeah, let's go to the Slack space. Quiz 42. Okay, it should be here. Yeah, quiz 42. Oh, ice slime. Okay. You know what? It's very close. It was not exactly what Polly had in mind, but I take this. I can take this as an answer. Yeah, because it does feel a little bit chewy. Yeah, bubble tea. Yeah, that's Polly's favorite drink. Yeah. 菜桶, there you go. Marshmallow chocolate milk. You know what? It does taste chewy, soft, but cold. Okay. Yeah, you can actually make it cold because most of the time when I drank chocolate marshmallow, I drank it warm. Okay, 仙草. Oh, you don't know what's in English. Okay. I don't know either. But I see. Okay. Yeah, pearl milk tea. Yeah, bubble tea. There you go. Team 12. Oh, okay. So, yeah, so this is something that I don't know how to translate either. I think it's a Japanese thing, right? It's also chewy to some degree. Bubble tea? Yeah, there you go. Hantian, I think that's a cool idea. Bubble tea, yeah. Well, we don't know if it's milky though. Somehow, Jason, you feel that, yeah, there's milk in it. Bubble tea. Yeah. There you go. Yeah. So quiz 42 here is to say this. Distance vector, of course, it made a decision locally based on the information it knows. But as time goes, as more neighbors telling more information, as the neighbors telling more, okay, the next time information, as the neighbor tells information more next time, okay, you as one of the scientists might get to know a little bit better the whole picture. Okay, so each time you get, only information from certain perspective, but as accumulate these information, you get to see the bigger picture. All right, but when you are making a decision, you are making a decision only based on information you know so far. All right. So you see that in distance vector routing, much like when you are doing quiz 42, right? At the beginning, if you see only it's a drink, but the range is so wide, you don't know what to do for sure, okay? And if you need to guess, then you can guess it's coffee, right? It's hot tea, okay? But next time when you see that, the second tester says cold, then it's probably not hot tea. Right? And then you narrow down on the choices. Yeah. So that's you know what, guys, the idea of distance vector. So let me play this very short video to tell the spirit of distance vector routing.
That should give you a rough sense how a router discovers a route without seeing the entire network topology. That is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be x and the cost from the neighbor to destination y. You can calculate the sum of x and y. If the value here is not infinity, you've discovered a route to the destination. But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, x and y for that particular neighbor. So you pick I such that xi plus yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hop that leads to the shortest path to the destination.
All right. And now finally, we can start talking about the distance vectors algorithm. And the first part is to introduce an equation called the Belmont equation.
And you see right on the slide that what I was describing is exactly how distance vector algorithm works. So we define the term here. dxy is the cost, okay, of the shortest path to go from x to y. And so what we're calculating here is the minimum cost to go from x to y, or to discover the shortest path from x to y. The way to do it is to go over all the v's. Okay, v's are the neighbors of the source. For each v, we calculate the cost to go from the source to the neighbor, plus the cost from the neighbor to the destination. So the sum here is the cost to go from the source to the destination through a particular neighbor v. So all we need to do is just to go over all the neighbors and calculate the sum for each neighbor and pick the neighbor that gives us the minimum value. And that minimum value is the minimum cost, okay, from x to y. And that v there is the next hop along the shortest path to the destination. So by doing this calculation here, we discover the shortest path. We discover the minimum cost. And This equation here is better known as the Belmont 4 equation because this algorithm implemented in distance vector routing is devised by these two great guys. Let's try to exercise the Belmont 4 equation using an example. And let's calculate the shortest path from U to Z. Right? The first thing to do is, hey, we need to have the neighbors, right, reporting, okay, how they know about the destination. So use neighbor including V, W, and X. So V will need to report the distance from V to Z, and that is the entry here. X will have to report the shortest distance from X to Z. Same for W to report the shortest distance from W to Z. And then we can begin doing the calculation. So we'll be going through all three neighbors one by one. So let's take the first neighbor V. Okay, so link cost from the source to V is 2. And dVz is 5. So we have 2 plus 5 here. Okay. From U to Z through V, the cost is 7. Second neighbor, X. So this is the second one. Link cost, okay, from the source to X, 1. And dxz reported as 3. So this is 4 here. Wow, nice. Third neighbor, W. Link cost is 5. And dwz, 3. So together, 8. So obviously, 4 is the minimum value. This is the minimum cost from U to Z. And you know what? X is the neighbor that gives you the minimum cost. Therefore, X is the next hop leading to the shortest path. So here, X here, achieving the minimum is the next hop in the shortest path. And that is also, okay, the link pointing to X is the link interface to insert in the forwarding table for destination Z.
All right. So that's the Belmont 4 equation. We're going to call that equation repeatedly in the entire DV algorithm. But the next video is a bit long, so why don't we take a break now? It's 11:07. We'll resume the lecture 11:17. Okay, so break now. All right, so let's come back. It's 11:17. Let's come back to the lecture. So there was a comment from external student here. Sorry, excuse that I don't necessarily pronounce your name correctly. Mafuz, I guess. Thank you for the nice compliment. And Catfish asked a question. Is it possible that the cost of network links changed during the link state report broadcast? It is possible. Yeah. So if that's the case, then the Dijkstra algorithm computes based on what the link state report reports. Therefore, the routes we came up with might not necessarily be the shortest. And so you can imagine how one sets the link state report refresh rate. Just give me a second. Let me stop the background music there, or background noise there. Yeah. So one wants to set the link state report update period to be shorter so that we don't miss the changes of the routes for too long. And exactly how long, it really depends on how frequent the route changes or how frequent the link cost changes. Okay. And I guess the frequency of link cost change really depends on the network administrator, okay, how they would like to control the routes. All right, I hope that answered your question, Catfish. And we can now finally start talking about the distance vector algorithm. If you recall yesterday when Polly was describing, there are two algorithms in the control plane, link state versus distance vector. Link state is global. And what global meant there is that we had the global graph information. But link state there, it's iterative, and it only makes decision based on information from the neighbors. It's very localized. Okay, so you see that why that distance vector, the description and the terms we use to describe this distance vector being so interesting. It's local and it's iterative. Every period you get to know more and get to know more, and eventually you also know, you discover what's the best. Okay, so that's the idea of the distance vector algorithm.
So that was the Belmont 4 equation, which captures nicely how one discovered the shortest path, the minimum cost to go from the source to the destination. But you see also in the previous example, right? Calculation of the Belmont 4 is actually based on these information, Cij, okay, the link cost from the source to each of the neighbors, and these, shortest distance from each of the neighbors to the final destination. That is also saying the distance vector algorithm as a whole contains the Belmont 4 algorithm. But before the Belmont 4 can be calculated, each node will also need to collect these information. Now this is actually configured in from the network admin when the network is established. Now this actually relies on the neighbors, okay, sending their routing information to the node. So next, what I'll be talking about is to go over the entire distance vector routing algorithm, covering both the message passing part as well as the Belmont 4 part. Now, before I talk about the entire distance vector routing algorithm, let me introduce just one more notation. dxy is the shortest distance from x to y. This is not new. The new one is here. A node is going to maintain the shortest distance from itself to every possible destination existing in the network. So capital N here is the set of the nodes in the network. So we do have multiple values of these dxy, okay, because there are multiple values of these y's. So each of these values is the distance, the shortest distance to a destination in the network. Therefore, we call this a distance vector. It's denoted as capital D. Okay. Now, because this is the distance vector for node x, therefore it's called the dx. So the distance vector routing algorithm, the goal is to derive dx, okay, for each node x, right? And before we could calculate dx, okay, the node here needs to have two pieces of information. Okay, according to the Belmont-4 equation, we need to know the link cost from the node to each of the neighbors. So CXVs. Now, in order to have the shortest distance from each of the neighbors to a particular destination, yes, we need to also know the neighbors' distance vectors. So for each V, no X here also maintain dV. And now the algorithm of distance vector. You see here, the key idea is it works in two phases. First of all, each node sends its own distance vector to the neighbors. So this is the message passing phase. And then two. Yeah, when the node receives the distance vectors from all the neighbors, yeah, Belmont-4 equation calculation begins. And as a result, okay, the node X there discover its own distance vector. And we could loop back. Okay, this node here then will pass the dx to the neighbors. That is the general idea of distance vector routing algorithm. The Belmont-4 equation, now this is the Belmont-4 equation. Okay, know that when X receives all these dv's from the neighbors, dx is not just one value to one particular destination. So this Belmont-4 equation is going to be called, again, these many times, so that we derive the shortest distance to each of the possible destinations in the network, N. Right. Yeah, final note here. Under minor natural condition, the shortest distance from X to Y, at the beginning, it might be really, really bad. Okay? But as time goes by, it's going to converge to the actual least cost. So minor natural conditions means that, yeah, for normal internet operation, this is going to hold true. To be more precise, this is distance vector routing algorithm, and it's depicted such that it looks like it's working in cycles. So each router in the network operates such a cycle. First, it's going to wait for one of these two events. Very common is that you receive a distance vector from the neighbor. Occasionally, this router here might detect there's a link cost change among these links to the neighboring routers, because these two events might affect the result of the Belmont-4 calculation. Yeah, so when these two events occur, we trigger Belmont-4 calculation to begin. As a result, we get a new distance vector. Now, if the distance to any of the destination has changed, that means, better route discovered, shorter distance discovered. Then we tell to the neighbors, because the neighbors might also benefit from the good news, benefit from the discovery. Right? So you see, distance vector routing algorithm working this way, it's iterative, meaning it works in cycle. In each cycle, it can only be triggered by two kinds of events, link cost change and DV update messages arriving at the router. It's also distributed because one can calculate and discover a better route and pass it to another node. So each node notifies the neighbors of a better route, and the neighbors then calculates even better route and notifies the neighbors. So in the end, they converge to the shortest path, but the effort is actually shared, distributed, and contributed by all the routers in the network.
All right, so that was the algorithm. And please excuse a internal student here. Sometimes she is a little bit of a trouble. I couldn't get her out of the room because she will meow from outside. So just ignore her, pretending that she's one of the students. Next, don't worry. So the distance vector algorithm is essentially straightforward, right? Each node, every now and then, broadcast the distance vector. And the nodes that receive the distance vector then check, right? With this new information, do I discover better route to a certain destination? So that's the idea of the distance vector algorithm. Now, let's check out an example and see if you can do the Belmont-4 equation calculation. All right, so this is the first video.
Okay, example time. In order to make sure that you understand this thing clearly, let's use a concrete example. So the example this time, very simple, only 3 nodes, X, Y, Z, and they are fully connected. Oh, by the way, we have not yet talked about initialization of the distance vectors. In node X, the distance vector of X is initialized this way. For destination X, well, it's itself, therefore, distance 0, it does not cost anything. okay, to transfer data from x to x. To go from x to y, let's initialize it to the link cost of xy if they are adjacent to each other. So 2 here. xz, so xz, they're adjacent, therefore we use the link cost between x. Similarly, you do the same thing to initialize dy for no y, dz for no z. Now, hey, in no x, it maintains all neighbors' distance vector, alright, but at the initialization phase, no x did not receive anything from y nor from z yet, so dy and dz, these two vectors, are left null. Okay, so I'm just using the sign of infinity there, okay, to represent their null. Similarly, for dx and dz in no y, and so on and so forth. So this is how you initialize, okay, the initial distance vector table, which is composed of 3 vectors. Okay. You maintain your own vector, you maintain also the neighbor's vector. Now, once, okay, the vectors are initialized, each router will want, okay, notify the neighbors. So this vector here will be sent from x to all the neighbors, y and z. Similarly, no y is going to send its initial table to x and z. And similarly, z sent to y and x. All right. And that's why, okay, in the next cycle, no x here in the table is going to see dy from no y, dz here from no z. All right. Now, with neighbors distance vector in place, now we can begin to calculate dx. So what is the value of dxy? What is the value of dxz? Now let's start from calculating dxy. Right? So the Belmont 4 equation says we try through all the neighbors, okay, of the source. X is right here, the source, 2 neighbors, y and z. So yeah, we do have 2 entries here. Okay, one is assuming neighbor being y. Second, using neighbor z. So, okay, for the first sum, we use the link cost from the source to first neighbor, and then adding the shortest distance from the neighbor to the destination. Now, in this case, neighbor happens to be the destination, so this is 0. Okay, as dy y says 0. Link cost xy, 2. So 2 here. Now, for the second neighbor, z, link cost of xz, 7. So 7 right here. Shortest distance from neighbor z to destination y. Okay, then we need to look up the table. From z to y. Right here, it says 1. So 7 plus 1. This is 8. And this is 2 only. Therefore, y here wins. Okay, y is the next hub router, okay, to y. So therefore, we write 2 right here, okay, for x, y. And now we derive dxz. Okay, so from x to z. Again, from the same source, 2 possible neighbors. One is y, the other is z. Link cost from x to y, 2. So 2 right here. Shortest distance from y to z, we'll have to look up the y row here to z. So the distance vector from the neighbor y suggests it should be 1. That's what we are seeing here. Now for the second neighbor z, link cost from x to z, 7. So 7 here. The shortest distance from neighbor z to z, trivial. And yeah, it should be 0 here in the table. So this is 7 and this is 3. Therefore, y wins again. To go from x to z, take this path. And we can add 3 back to the distance vector of x. And what do we do next? Yeah, now x here acquired the new distance vector. It's going to what? Send it to all the neighbors. Okay. So this is the first cycle, calculating the dx, okay, from the x's point of view. Similarly, no y there is going to be calculating the dy, No z there. It's going to be calculating the dz because it's receiving dx and dy.
I see what's wrong. Yes, I was muted. I was muted. Um, yeah, but hey, real quick, this is quiz 43. Thank you guys. I know that you guys are listening this way. No, I just forget to unmute myself. Quiz 43. We use the same example, but we exercise doing the Bellman 4 equation computation for no z. So we just did the no x's table, right? In the example. Let's now do no z's table. Okay. And that is essentially calculating the dzx and dzy entry. You see that in no x's case, we calculate the dx, isn't it? And inside dx, dxx entry is always trivial, 0. So you calculate dxy and dxz. For z, dzz is trivial, so you calculate zx and dzy. And for this, let's give it 10 minutes so that you guys can make sure that you pick up Bellman 4 equation. Okay. Please try to make sure that you do it yourself so that you can save a lot of time trying to review what distance vector is doing in Bellman 4 equation before the exam. All right. So go to channel W14, quiz 43. So you guys have 10 minutes. That should be plenty for each one of you to exercise, calculating dzx, dzy based on the Bellman 4 equation. Let's start. Well, what am I kidding? Yeah, you guys seem to pick this up very well. But you know what? Team 7, Team 8, Team 2, Team 10, and Team 5. Yeah, try if you can calculate dyx and dyz for y's table. Okay, those who are done with this, I know that it's probably too easy for you, but try calculate the table for no y and let me know. And I think for no y's is dyx, dyz. I think you can just reply to your own post earlier, and that way I see. Okay, and let's see. Which one gets y's table first? Yeah, amazingly fast. Okay, the first one get dyx, dyz out, gets the bonus. Let's see. Oh, okay, coming. Cool. You know what? I think you are right. You are right. Yeah, Team 10 gets the bonus this time. Very well done, Keke. You obviously follow the videos very well. I thought that those are hard. Oh, Yujie, very good. Okay, Team 14 also gets the bonus. Well done. Cai Tong, very good. Well, okay. So it turned out that we only need 5 minutes. Well, less than 5 minutes. Yeah, so very good. I see that at least many of you have already captured what distance vector is doing and how to do the Belmont 4 calculation. Okay, but still, let's go through the video that Polly shows how she derives dz. Okay,
Let's try to calculate the distance vector of z together. So you see, it will be the shortest distance from z to every possible destination in the network. And in the network, it's very small. Starting from z, there are only two possible destinations, x and y. So we just need to calculate dzx and dzy. Now let's calculate dzx first. According to Belmont 4 equation, okay, so what we do is to try to find out, okay, through all these neighbors connected to the source, okay, which one leads us to the shortest path to the destination x. Now, in this network, we do have two neighbors, okay, connected to z. So let's try the first neighbor first, which is z. So we'll be using the link cost from the source to the neighbor. So link cost from source to neighbor, z to x being 7. And then based on what the neighbor knows, okay, the shortest distance to the destination. In this case, neighbor is x, destination is also x. Now we look up the table. So dx here being known to z, according to that, the xx is 0. Now the second entry, the second neighbor is y. And so we'll then take link cost from z to y, which is 1. And then based on y knows the best to the destination x. So dyx, okay, is the value we need to add link cost zy to. And according to the table, okay, dy says dyx being 2, therefore 1 plus 2. So Going through x, we get a pass. The cost is 7. Going through y, we get a pass that the cost is only 3. Therefore, 3 wins. Okay, so you see here, to go from z to x, the shortest pass distance is 3. And the next hop is obviously y. Now let's just calculate the other entry, which is zy. Let me clear the markup first. All right. Okay. Again, according to the Belmont 4 equation, source is z, and the destination we wish to find out the shortest path cost is y. Yeah. In the Belmont 4, we'll try, right, for 2 different neighbors in this network of z and c, which lead us to the shortest path. So let's try the first neighbor here, x, link cost being 7 again, and then, what about dxy? Now let's look up the table. It's dxy, therefore, yeah, the shortest distance is 2. So we ended up adding 7 to 2, which is 9. That doesn't look so good. What about the other neighbor of z? zy is 1 again. What about the shortest distance from y to y? And hey, it's itself, so y to y, the cost is 0. So okay, this other path going through y give us only path cost 1. Therefore, yeah, going through y, this give us shortest path from z to y. And therefore, we update the entire dv, which is now 310. We can actually continue and calculate what is dy, isn't it? So there are again 2 entries, yx and yz. Let's calculate yx first. Okay, this time y is the source and destination is x. Again, we need to try through all the neighbors of y. So let's start from x. Okay, so x in the middle, source being y, destination being x. So we go through link yx, which is 2 here, and then find out what is the shortest distance from neighbor x to the destination x. So neighbor and destination happen to be the same node. According to the table, x, yeah, the value is 0. So here, going through neighbor x, ooh, nice, total cost is 2. The other neighbor, so y's other neighbor is what? Z. So z in the middle here. Link cost yz, 1. What about the shortest distance z knows to the destination x? So dzx, we'll have to look up the table here. Dzx, which says 7. So the best path, okay, going through neighbor z is unfortunately, yeah, costing us 8. So comparing the two, yeah, the path going through neighbor x is better. Okay, so yx and then reaching x. So total cost 2. So we can now update, yeah, dyx to 2. The second entry in the distance vector of y is dyz. Okay, so again, starting from y, going to the final destination z. So starting from y, and this time final destination z. We'll have to try through both neighbors. First neighbor being x, link cost from y to neighbor x is 2. The shortest distance from x to the final destination z, oh, dxz. So let's see, dxz. Yeah, the entry in the table says 7. Second neighbor being z here, so yz, the link cost is 1. Nice. What about the shortest path from z to the final destination z? Yeah, it's actually quite straightforward, isn't it? zz, trivially 0. And 9 comparing to 1, which one is shorter? 1 here. At this point, we can also update the entry dyz. And this is how we come to the distance vector of y. So we now finish deriving all the distance vector tables at time t1. What you see also is this. Look at this. dy and dy, okay? Between t0 and t1, dy did not change. Therefore, dy here, no y here, does not need to propagate the data, okay? Propagate the vector to no x and no z. While, okay, when x here finds out the dx, which is different, okay, from t0's dx, we'll need to propagate dx to no y as well as no z to calculate the table for t2. Similarly here, z find out the new dz being different from the old dz will need to propagate also. Okay, dz to know x and know y. Therefore, the two other nodes can calculate if the dx and dy needs to be changed further.
All right. So that was a full computation at T1. Now there's just one little video left to tell more about T2.
So after the quiz, you'll see dx is changed and dz changed as well. So no x and no z will be propagating, okay, the newly discovered, the better distance vector, like this. Okay. So no x receiving the update is going to replace this with a new distance vector. Just like y here, okay, this vector here is going to be also replaced with a new vector from z. Similarly, this vector here is going to reach z, and z is going to update from 027 to 023. Now, what's a bit special is this. Okay, in the quiz, you see that dy here at no y is actually not changed. Therefore, no y here is not going to distribute to 0, 1, okay, to x nor to z. So this stays the same. Therefore, this and this stays the same. But no y here is going to receive a new dx and new dz. Therefore, this gets changed to 023. This gets changed to 310. You see that in cycle number 2, x, y, and z, they actually converge. Okay? The view is consistent, and they all converge to the shortest path, okay? The least cost path. So in this very simple example, we see distance vector using the Belmont 4 equation works really well. Converges in 2 cycles.
All right. And next, just like when we finished talking about link state algorithm and walk through the example, we discussed the issues. Okay, distance vector has also an issue, and it was a quite serious issue. Okay, so the issue concerns mainly about in case there's any link cost change or path change. Okay, would the whole network update to the change? The easier case is that if the change is good, for example, the link cost dropped from 5 to 1, for example, okay, then it's okay. Usually good news, good change, propagate very fast. Okay, so that is this property called good news travel fast in distance vector.
So one very interesting property with the distance vector routing is this. Whenever there's a good news in the network, it travels really fast. Okay, so when there's a better route, it gets propagated really fast and everyone converges really fast. But if it's bad news, meaning if a route suddenly go bad, okay, it will take a long time for everyone to discover, okay, the route is really bad and we should really be going another way. Okay, so let me describe the first case, the good news travel fast case. So recall. Okay, this is the change where the link between x and y is reduced from 4 to 1, so good news. The node is going to detect local link cost change and update the routing information and trigger Belmont 4. If the distance vector changes, then send to the neighbors. So here, link change from 4 to 1. So at time 0, y is going to detect the link cost change and update its DV and inform the neighbors here and here. So next point in time, z here is going to receive this distance vector from y. Okay, it's going to see, oh, the shortest distance from y to x is now 1. Okay, therefore, z is going to update the shortest distance to what? 1 plus the cost from going from y to x, which is 1 now. That is 2, which is better. Okay, so z is going to update its own dB and send it out to the neighbors. And y is going to receive z's update. Z says, okay, the shortest distance to x from me is 2. And y sees that, hey, I don't have a direct connection. My shortest distance is already 1, right? Your shortest distance to x is 2, plus the link cost from y to z. This path is not better. Okay, so y there will not discover a new path, okay, a better path to x. Therefore, distance vectors stay the same. Okay, no more message being sent out. Okay, back to Z. Network converges. Everyone goes to the steady state. The second case is the bad news travels slow. So you see from the scenario, the link cost, instead of dropping to 1, now goes up to 60. Super bad news. Of course, X and Y here would detect there's a link cost change. But in this scenario, it would take us 44 cycles until the network goes back to the steady state, until they all converge to valid shortest path. Okay. Now, bad news travels slow, meaning routes converging slowly. Okay, that is also referred to as the count to infinity problem. Now let's go to a quiz to see what's going on there. Okay.
There we go. The quiz right here. Bad news goes slow. All right, so this is the same example, except that the link cost goes from 4 to 60. So the link cost between X and Y, this is a bad news. Okay, so, okay, right after the change T0. Okay, so poly will try to derive X's table right after change T0, and you tell, okay, Y's table right after the change. So let me see, yeah, it'll be like this. So poly tells the table, okay, at X, and you try to derive the table at Y. And so let me play the video that poly derives the table at X.
Yeah, quiz 35, the scenario is a bit tricky.
Oops.
Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from the dx. Let me just show the final result real quick. Yeah, the xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So the xy, the source is x, destination is y. Through two neighbors of x of the source, that would be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through the first neighbor y, what is the perspective? What is the shortest distance to the destination? Well, y to y, we'll have to look up the table coming from no y in order to find out, right? That is y's perspective. So that's in dy came from no y earlier. So dy y, then it's 0. And then, yeah, for the second neighbor, z, what is z's perspective, the shortest distance to y? That will be what? dz, yeah, to y. So dz to y. And that is in, distance vector of z came from no z earlier. Z to y, yeah, it says 1. So we put 1 here. So sum of trying through neighbor x, 60. Sum of trying through neighbor z, 51. Therefore, yeah, no z here wins, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z, link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z.
And now let's go to quiz 44 to try to find out what is the table for y. Okay, so let's go to the Slack space. It's W14 quiz 44. Yeah, I know it's a little bit unexpected because you guys are doing exceptionally well with the previous quizzes from 39 to 43. So This week, by Saturday, there's one more quiz for you to complete, which is 44. All right, so this one I would say that it might be a little bit harder for you guys. Let's give it some 10 minutes and see. Well, if you guys came up with the solution earlier, feel free to type them up. Okay. Yeah, I see you guys. So came up with the solution, say suggesting dyx is 51 and dyz is 1. You know, you know what, guys? Very good effort. Very good effort. Um, but let me show the second half of the video that derives the table for t. Let me see. I think it's t0. Okay. You'll see it's actually not quite. It's actually not quite. This is what's tricky about distance vector routing. Okay, so let me show you the part that poly derives table for y at t0.
Yeah, quiz 35, the scenario is a bit tricky.
Yeah, so let me skip to the second half of the video. And now.
Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is as a human, you see the global topology, you know it's 60, but distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful, and then still walk through the Belmont 4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cos is link cos yx is 60, link cos yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Belmont 4 equation says comparing 60 to 6 wings. Okay, and that is actually going through no z. So y is going to pick. Okay, saying to go to x, let me send it to z first. And then z says, I know a way to x, which is, yeah, the old impression, right? This way. So you see the packet there is going to go y to z, z to y, but y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector, okay? Before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the odx and odz. Okay, and right at the link cost change, no y, okay, have not yet received the new dz, new dx yet. So y is going to be using the odz and odx. Therefore, you see, okay, the odz is telling y the shortest distance from z to x is 5 here. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x.
So there you see that it's very easy that human beings see the entire information and use what we know better, okay? But distance vector as a router, we don't know. We can only base decision on what's known to us, to the router. Okay, good. So guys, try to update your solution for quiz 44. We'll definitely exercise a little bit more about bad news travel slow next week. Okay, and that's all the time we have for this week. Once again, thank you very much for your participation. The music seems to have a lot of noise. Yeah. Sorry about that, but I think I terminate that Yeah, so it should be clear now. Okay. All right, so that's all the time we have for this week. Try to update your solution for quiz 44. And think about this a little bit more. Okay. We'll definitely exercise more next week. And that's all. Bye. I know, tricky, isn't it, distance vector? Especially when it's bad news travel so. So do you all hear the noises when I play the Jeopardy music? So in case you do, please let me know. Oh, okay, okay. Oh, I'll let her know. Yeah. Yeah, she's very playful. That's all I can say. All right. And guys, let me know in case you also hear noises from playing the Jeopardy music. It could be because the equipment I have here is a little bit more sensitive, okay, than the equipment I have in my office. Okay. Bye, 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 guys. I see. Okay. Okay, I'll see what I can do. I see. Okay, I'll thank you for the feedback. I'll see what I can do and try to eliminate the statics. Okay, good. Bye. And let me end the stream here.